Hello everyone. In this lecture we are going to discuss about impact of jets on curved surfaces or curved plates. In the previous lecture we discussed only about flat plates, either normal or inclined to the jet. But in this case we'll see what will happen when the surface that a jet will hit is having some curvature. So let's consider this kind of a curve where the direction of the deflected jet depends on the shape of the curve. So if we consider a jet hitting this surface, and depending on the curve it will be deflected in this direction, on the other side it will be deflected in this direction, and you can see that the directions are different. One is getting diverted by this much angle, the other one is getting diverted by a greater angle, and so on. However, the force acting on the plate due to the strike of the jet along a given direction can be calculated based on the rate of change of momentum of fluid in that direction. So when this jet is hitting this plate, if you want to find out the force in this direction, this along the direction of the jet, say, then we'll have to find out what is the rate of change of momentum in this direction. So we'll find out what is the initial momentum, which is rho a v square, as we have established earlier. So, and what is the final momentum after the water leaves this plate. But the problem is that this portion of water is leaving with a different momentum than this portion of water because their directions are different. So what we'll do is we'll try to approach some simplified problems instead of this kind of a difficult problem. Let's see why it is difficult. This is only a two-dimensional representation. So if we want to have a 3D representation, then let's say the plate is something like this, which is a cut portion of a cylinder maybe, and on this plate if a jet strikes at a certain, suppose normally, if it hits here, then what will happen to the water is that some water will get deflected in this direction, some water will get deflected in this direction, some water will get deflected in this direction, which is perpendicular. Same is true in the other direction, which is again perpendicular, but this angle and this angle, they are not perpendicular, and there will be all the directions in between. Like this. So it's difficult to find out how much water is deflected by what angle, and therefore we are not going to deal with all in general shape of curve, but we are going to be stuck with some specific shapes of curves, and that is symmetrical curves. By symmetrical it means symmetric about the axis of the jet. That means if this is the axis of the jet, then the curve needs to be symmetrical around that axis. So we're going to consider a jet striking this kind of a plate at the center, suppose. So when it hits the surface, the inner side of the surface, inner pole maybe, then water will come out of this jet in these directions. And the convenience with this kind of a symmetrical plate is that all these directions, this direction, and this, they will be making the same angle theta, or let's say this angle with the original direction. So they will all be deflected by the same angle, and if you practically try to see it, it will be looking like a sheet of water, or rather a cone of water coming out of this plate. So this because of this constant angle convenience, we are going to use this kind of a symmetrical plate. Now if we could consider this kind of a plate, then we have already seen what happens, because the angles are all different and it's very difficult to find out how much water is getting deflected by how much angle. Okay, so we'll try to deal with the mathematics of this kind of a symmetrical plates hit by a jet. So jet striking normally at the center of a symmetrical concave vein or plate. So this is the plate which is struck by a jet like this at the center. So in two-dimensional it will look something like this. Now force will be again rate of change of momentum, which we are trying to find out. Initial rate of momentum is rho a v square, where a v square is the volume per unit time or discharge, that multiplied by density gives us mass per unit time, and again multiplied by another v will give us a v square. So a v is q and rho is density multiplied by v is momentum. Now final velocity is equal to initial velocity. That's an assumption that we are making. The meaning of the assumption is that the velocity or the speed at which this jet comes out of this plate is equal to the original speed of this jet, and we are making this assumption to simply make our calculations easier. And the underlying assumption is that there will be no friction along the surface of the plate. That means the velocity at which it has hit the plate, it will leave the plate at the same velocity, same speed rather. But in reality, the final velocity will be actually less than the initial velocity. But that leads to a little bit longer equations, so we want to avoid that. We want to be satisfied with a shorter equation. Then final rate of momentum will be rho a v, which is mass of liquid leaving this plate per unit time multiplied by v cos theta. Now v cos theta is the component of the velocity in the direction of, in the original direction. So if this was the direction original of the jet, and after water leaves in this direction, so this angle is theta, and so we are going to take component of this velocity in this direction. So, and cross-sectional area of the jet is equal to cross-sectional area of liquid leaving the surface, and that's understandable because we have considered that the velocity is also going to be the same, and therefore from continuity equation a1 v1 is equal to a2 v2. Since we have considered that v1 and v2 are same, that means there is only going to be one v, therefore a1 and a2 must be same. Now if we want to have a better idea what are a1 and a2, that is a1 is simply the area of the cross section of the jet. So if we have a jet like this in this direction, so suppose the jet area is a circular cross section, and after it hits the surface it will bounce back like this, and it will be leaving out with this kind of a cross section after leaving the plate. So by cross-sectional area we mean this cross-sectional area compared with cross-sectional area of this ring or this conical sheet of water or maybe cylindrical sheet of water that's coming out of this this plate. So this area must be equal to this area. So that's what it's meant by the cross-sectional area of jet equals cross-sectional area of liquid leaving the surface. Now after that, the rate of change of momentum is initial rate of momentum per unit time minus the final rate of momentum leaving the plate, which is rho a v square cos theta, and therefore finally we have the force equal to rho a v square into 1 minus cos theta. So this is how we find out the force acting on a curved surface which is symmetrical around the axis of the jet. Now a special case may be mentioned here, that is if we have a plate where, suppose a hemispherical plate, in case of a hemispherical plate which is half of a sphere, this angle by which the jet will be deflected will be equal to 180 degree. This is the original direction and this is the final direction. That means our theta is going to be 180 degrees. And when it is 180 degrees, then we'll see that simply by putting that value in this formula that we derived in the previous slide, we'll put cos 180 degree, which is minus 1, and so finally it becomes rho a v square, 1 minus minus 1, that's 2, and we are getting twice rho a v square, which is the force. Remember, in case of a flat plate which was hit by a normal jet in this direction, it got deflected by 90 degrees and we got a force equal to rho a v square. But when we can deflect the jet by 180 degrees, in that case we are doubling the force acting on the jet. So if we want to utilize the force of a jet, then we'd want to use this kind of a hemispherical plate which diverts the fluid by 180 degrees. Any other angle in between 90 and 180 degree will give you some value between rho a v square and twice rho a v square. So that will be the case for any plate which will be shaped like this or this. So this plate will be having some force which will be slightly more than rho a v square, but this plate is now deflecting by a greater angle, so this will be having a greater force than this plate, and the maximum will be when it is completely deflected in the opposite direction, that is in case of a hemispherical plate. It's not necessary that it has to be hemispherical. It could be half of an oval shaped object. It means it can be like this. Here also it will be deflected by 180 degrees, but it's not exactly what you'd call a hemisphere. So the basic principle is that the greater the angle by which we can deflect it, the more will be the force acting on the plate. So maximum force is exerted on the plate when the jet is deflected by 180 degrees. Now let's try to understand another example where the jet strikes a curved plate tangentially. By tangentially, we mean that instead of hitting it here on the surface, it hits on the edge somewhere around here. Now what happens in this case? The force is equal to rate of change of momentum. That is always applicable, and initial rate of momentum is again rho a v square. Final rate of momentum is again rho a v square cos theta, which was the case in case of the previous case as well. But the advantage in this case is that the water doesn't get spread out after hitting the plate in tangential direction. If it was, let's say, take this example, if it was hitting the plate somewhere in the middle, then water will be deflected in this direction, this direction, this direction, this direction, and all the other directions in between. But if we are considering the plate which is, or a jet which is striking the plate on the edge only, that is tangentially, somewhere around here. So after that, it will not get deflected in these directions. It will simply be gradually deflected along the curve of this plate. Same will be the case for this plate as well. So if it is hit by a jet like this, right at the edge, at the inner edge, then it will get deflected. I cannot show it here. Something will be happening inside, and when it comes out, it will come out like this. Now it will not come out using this kind of a circular cross section. Obviously, the stream of the cross section of the jet will be slightly flattened, so that will be coming out somewhat like this. In this case as well, it will be coming out like this. So what the advantage is that there is not a lot of deflection in all these directions. Whatever flattening is occurring, that is negligible, and therefore we can only deal with one angle theta, and that angle is simply, if it is getting deflected by this much angle, it is this angle theta only. So final velocity and initial velocity are same. That's the assumption. That means along this surface we have not considered any friction, and therefore the velocity or the speed will be the same when it leaves this surface. And therefore also cross-sectional area of jet is equal to cross-sectional area of the liquid leaving the surface, which again means this cross-sectional area, the circular cross-sectional area, should be equal to this flattened cross-sectional area, or in this case this flattened cross-sectional area. So this area and this area, they are same. Also this area and this area, they are also same. After that, force is again equal to rate of change of momentum. So we have what is the initial rate of momentum minus the final rate of momentum, and that will give us the same formula as before, which is rho a v square 1 minus cos theta, where we have to remember the theta is angle by which the jet is deflected from its original direction. That means this angle is theta. Now we can have different types of curves where this is only deflecting this jet by a small angle, which is this angle, which is even less than 90 degree. But the maximum we can get is when we hit this along a hemispherical plate or a plate which can deflect the jet by 180 degrees. So in this case, we'll get the force just like before, twice rho a v square. So in this case, it will be rho a v square 1 minus cos theta. And as you can see, as theta becomes 0, that means if we have a plate which is completely straight or only slightly curved, and on that plate, if we try to hit the jet tangentially, then it will get diverted only by a very small angle, which is this angle, and the force will be very small. And as it tends to 0, the force also tends to 0. 0 because cos theta becomes 1, cos 0 becomes 1, and that gives you 1 minus 1. So this whole term becomes 0. Now one question may be, why would you study tangential impact of jet? I mean, it's very impractical to aim a jet exactly at the edge of the plate, and it's not even possible because some part will always hit. Suppose if you're aiming for this plate, then some part will always hit this portion and get deflected in this direction. So why are we studying it then? The reason is that in some turbines, instead of using a hemispherical plate, we would use a plate which is shaped like this. And the jet will strike at the middle approximately. And when it strikes at the middle, it gets divided into two streams. One stream gets into this part of the plate and gets deflected in this direction. The other part goes along this direction and gets deflected in this direction. So if these two directions are 180 degrees, then we'll be getting the same twice rho a v square amount of force. But one thing we are reducing is that compared to a hemispherical plate like this, is that the impact at the middle, because at the point of impact the water gets deflected by 90 degree very suddenly, and that causes a lot of loss, and because of the impact some additional loss takes place in terms of sound and vibration as well, which is avoided when it is striking the jet tangentially, and it will be tangential to two different curves. One curve is this part, another curve is this part, and this edge is a very sharp edge. So we'll study about these things later when we go for study of hydraulic machines. So again, we'll leave some I'll leave some problems, numerical problems for you in Google Classroom, and that's all for this topic. Thank you.